Traveling at the speed of ideas on the Knowledge Transfer Exchange. Brought to you by the Florida Department of Transportation, the Training Development Team, and the State Office of Construction. David Sadler, Director, 605 Swan Street, Tallahassee, Florida, 850-414-4150. And now, today's guest.
Hello and welcome. Today we're going to be talking about pre-stressed construction, what it is, and why it's of importance, especially in the state of Florida and as it relates to Florida's transportation system. My name is John Westfall. I work for the Florida Department of Transportation, State Construction Office. So let's get into it. So post-World War II, pre-stressed construction played a pretty vital role in the interstate highway system that was promulgated by President Dwight Eisenhower. Consider all the bridges that you drive on and under and along. More than likely, if you've come to work today, you've traveled and it was over a bridge, it was likely over a pre-stressed concrete girder bridge. It's a very prevalent bridge type, superstructure type that's found virtually anywhere in the state. It is the workhorse superstructure type in Florida, and that's owing to its ease of construction and ability to be erected in a fairly straightforward and easy manner. Non-pre-stressed or conventionally reinforced or mild reinforced concrete, typical spans, max spans would be anywhere in the mid-30s to mid-40s at the absolute max. For a flat slab type superstructure unit, pre-stressed girders can range anywhere into the high 100s and low 200s. The idea of pre-stressing was thought of long before material technology made it feasible. The physics have been there all along. It just took some time for the materials to catch up. A man by the name of Eugene Fresnay was considered as the inventor of the concept. Mr. Fresnay. The first U.S. bridge that was built was in Philadelphia, Pennsylvania in 1951. Here's a picture of the Walnut Lane Memorial Bridge. This bridge is no longer in service and has been replaced. However, observe how similar this bridge looks to any bridge that you drive on or drive under even now. It doesn't look altogether very much different. So to go into a little bit more detail as to what makes it different from typical reinforced concrete. Pre-stressed concrete uses strands rather than bars or rebar that you see all the time. Beams and piles are typically built at precast yards and shipped to project sites. So there are three major ways in which these two methods of reinforcing the bridge differ from one another. For one, consider the geometrics. Pre-stressed strand is just that. It is a 7-wire helically wound system and is not a solid cross-section. The two materials are made differently and thus have different material properties. Third, and most importantly, as the name denotes, strands are tensioned before concrete is placed. So we keep saying pre-stressed concrete. There's a reason for that. And this is to just give you an idea of what strand looks like. As I said, it's a 7-wire system, 6 wires wrapped around a king wire. And then on the right, typical reinforcement, rebar or mild steel, are solid bars with these ribs around them. So because pre-stressing steel is tensioned or stressed, it has to behave differently. This is what I alluded to earlier about the material technology needing to catch up with the physics. Rebar is a grade 60 material. Its yield stress is around 60,000 psi, or to abbreviate that, 60 ksi. So it's basically kilo psi. Pre-stressing steel, on the other hand, is grade 270, meaning its yield stress is 240,000 pounds per square inch, or 240 ksi. This is fine and great, but what is yield and why is it important? Well, it's hugely important. We'll get to that in a moment. And it's partly the reason why pre-stressing is able to do what it does. Consider a bar that has a cross-sectional area of 1 inch squared. Stress is simply equal to force over an area. F, stress, is equal to P, which is your force, over A, your area. So, pretty straightforward computation. We have 60,000 psi divided by 1 inch squared. Yields a stress of 60,000 pounds per square inch, or psi. Graphically, this is what that looks like. Consider a cylindrical bar with a force P exerted on it. That P is exerted over that cross-sectional area A, which you may or may not remember from your math class. The area is equal to pi times your radius squared. What is yield? This is the best definition that I could find, courtesy of Merriam-Webster. Yield, in an intransitive verb sense, somebody out there can check me on my grammar, but in this sense it is to give way under physical force, such as bending, stretching, or breaking. Another example for you. Let's consider a bar of steel. Let's consider a tension that is applied to that bar, a tensile force, stretching and pulling that bar. If you release the tension, the bar is going to return to its original length. That pull or elongation is proportionate to the force applied. So you can pull and release on that bar all day until you pull too far and you've yielded it. Throw some more equations at you here. So consider the same piece of bar. You apply a load P to it. It's going to deform. That squiggly looking upside down Q kind of thing, that's a Greek letter delta. So that's the change in length with a given force. So this says your change in length, delta, is equal to your force times your length over your area times a constant for a material, E. We won't get into that exactly, but that gives you an indication as to how stretchy a material is. And each material has its own E. What E is modulus of elasticity. So yield stress is a limit. Every material has an inherent limit on its yield. So let's look at the differences between rebar and strand. Rebar is going to yield at 60,000 psi, whereas the strand yields at 240,000 psi. That's over 4 times the difference, 4 times greater yield. That means you can stretch and pull on that strand with a higher load for a given area on strand, and it's going to release and return back to its original length. You cannot do the same thing with rebar. What this means is if you pull on a bar greater than 60,000 psi for a grade 60 material, you've yielded that bar. So the benefit is that strand, you can pull it with a greater force, and that's what ultimately makes it able to work, what makes the physics work behind pre-stressing. So stress beyond yield, it won't return that bar, that piece of steel is not going to return back to its original length if you've gone past yield, that yield stress. As I said, the 60,000 psi for normal steel, 240,000 pre-stressing. You can pull on that bar past yield, but your elongation is not going to be proportionate to the force. And like I said, when you let go of it, it's not going to return back to its original length. You keep pulling on that bar, and material failure will occur. So big picture, what are we looking at? Let's consider a tension bar of steel that's not released. So what if we place concrete around that bar and let that concrete harden or cure and bond to the steel? And then we cut or torch the bar. What's going to happen? Well, the concrete is going to bond to that stretched bar or that tensioned steel bar and will restrain the bar from returning to its original length. So what does that do? That's ultimately going to lock in that tendency of that bar to want to stretch back to its original length. That's going to be energy that's going to basically transmit into the concrete through the bond between the steel and the concrete. So this is going to result in pre-compression. Out in the field, out in a pre-stressed yard, this is what the anchorage system looks like of these strands that are tensioned. This is the dead end, if you will, of the stressing operation. The steel is being pulled on the other end. This is simply the anchorage point for a pre-stressed girder that is about to be placed. This is a better view of several strands that are being tensioned prior to concrete being placed. And then this is the final product. This is after concrete has been placed around those strands and has been cured, the strands have been cut, and now the beam is simply being stored until it's ready to go out to the project site. So fundamentally, all materials behave in a spring-like kind of a way. Consider various materials: wood, aluminum, concrete, glass, rubber, plastic. What happens when we push and pull on these materials? Well, as I said before, with this concept of modulus of elasticity E, every material has a specific ability to stretch, some better than others. Some are better at being pulled, some are better at being pushed against. Tension versus compression. So think about some of the materials you deal on an everyday basis. Are there some materials that might break readily when you go to bend it? Are there some materials that become stretchy or yield? Are there some that just fracture right away? Well, we reinforce concrete. But why? Why do we do that? Why are we always making such a fuss about reinforcing concrete? Well, truth of the matter is, concrete is a very brittle material. It's very good in compression. You can push on it, squeeze it all day. It's very good in that sense. However, when you go to bend it or put it in tension, it's not very good at all. And so concrete is what we would consider a brittle material. Steel, on the other hand, is a ductile material. It is very good in tension and will elongate quite a bit before it actually fails. So to make up concrete's poor tensile strength, we basically place reinforcing in zones of tension in concrete. Not only in zones of tension, but primarily that is the function of reinforcing steel. Reinforcing steel also tends to restrain cracking and is good at just providing an overall skeleton of reinforcing to keep the concrete from cracking in other ways, from shrinkage while it's curing or in creep, which is what happens when concrete is loaded. It creeps, it tends to move under a sustained load. So these other various mechanisms are why we reinforce concrete. So steel helps the concrete to behave when tension is applied. Put us back on track. To increase the tension capacity of a section of concrete, we reinforce with pre-stressing steel. We install, pull, form, place, weight, and cut. What does this look like? We have three graphics here. The top is a reinforced beam with just plain mild reinforced steel. The second one down is pre-stressed strand. Now you can see in that top picture with a given load that concrete will crack a lot more readily than a pre-stressed element will. In fact, because we put compression into the zone where that concrete is going to experience tension from a load, it doesn't crack under that load. So you pre-compress it kind of like an accordion, and then when it actually is loaded, it evens out. We'll come back to that. So let's go back a bit. In fact, let's go back thousands of years. We didn't want to use reinforcing at all. If we only had concrete to use, how could we form or shape the concrete in a way to make it behave? Ultimately, you got to ask, what would Spartacus do? Well, you guessed it, an arch. And if you didn't guess it, well, now you know. An arch is a shape that's able to accommodate loading without reinforcing. Because concrete is so good in compression, if you're to form it in such a way that it compresses on itself, then you don't need reinforcing. So when you're in Rome or Rhode Island, use an arch. This is a concrete arch bridge in Rhode Island. There are many like it in the state. It's an aesthetic shape and highly functional, and very durable, I might add. Here is now given this is a masonry arch, this is not a cast in place type operation. What you have discrete elements that are placed together. You don't even need to have material that's continuous. You simply need to be able to place it in a way such that you place those elements together, and when gravity does its thing and pulls it to the ground, it compresses the pieces together. That's why you're able to get this viaduct to work. Now, kind of the arch perfected in a way is a dome. This is where we have concrete all coming in on itself toward a center. You don't even need, obviously, that spot in the middle, because most of the tension is at kind of the midway between the bottom and the top of the arch. Most of that compression is there. This is the Pantheon in Rome. The man who did the Pantheon is the same man that did this bridge, which is no longer in service, of course. This is the man who built both of those structures, Polydorus of Damascus, or Jared Leto of antiquity, as I like to call him. Missing a nose, though. Here we have the Lawton Child's Memorial Bridge in Ocala, or not. Psych you out a little bit, make sure you're paying attention out there. No, this is a bridge in Switzerland, and if I'm pronouncing it right, it's a Salginatobel concrete arch bridge. Very scenic, very striking bridge. This bridge was built by Robert Maillart, a Swiss engineer. Here's just another humble example of a little stone arch bridge over a creek. Now, as I said, you are able to place single elements in such a way that these elements are restrained on the left and right by what's called thrust blocks. Keeps the arch from wanting to splay out. And because you restrain it in that way, when you apply that load, those pieces all bear in on one another. So if arches are incredibly efficient and are aesthetic, why don't we just build them everywhere? Why use reinforcing at all? Why use pre-stressing? Well, as you can see, or you may have observed, in order to get a given span to work, you need depth. The further the span in general, the deeper the arch. So you can see here, to accomplish this span, you need a good bit of depth. Consider the cars on the deck of the bridge, and just consider how deeper that depth is compared to the cars. You need a good bit of real estate, both vertically and horizontally. The horizontal thing is not the problem, it's more so the depth. Because we don't have valleys to traverse in our state, we have very few hills, mostly in the north, but certainly no mountains. We don't really have the space, and we don't really have the need. But what we do have the capability of, we're able to span these great distances without such a depth using the current technology out there. So consider this pre-stressed girder. Now this span is in the neighborhood of 191 feet. The depth of this beam is about 8 feet. So for a pre-stressed girder, that's a pretty deep beam. However, if it were an arch, it would have had to have been much deeper. So what this pre-stressing does, it forces the concrete to behave as though it were an arch. Well, you may be like these boys down here and say to yourself, that doesn't make any sense. How do we do that? Well, an arch is formed or restrained to be entirely in compression when it's under its service load. So how does pre-stressed concrete mimic this effect? Well, concrete is placed into compression throughout its entire length by pre-compression from the steel. The amount of needed force at the end depends on the loads directly related to span length, the self-weight of the girder, the deck, the barrier, the live load, utilities, etc. Going back to this graphic that we looked at before, as we said, without pre-compression, under a given load, the beam will crack. Even though it is reinforced, there will be cracking that results. However, if you apply a pre-compression to resist, and you can do this in a calculated way, you can calculate the amount of pre-stressing you need to counteract a given load, such that when that load is applied, you get no cracking. And the steel and the concrete work together. So bringing this around to Florida work, FDOT, what things do we do that are impacted or impact pre-stressed construction? We have specification 450, that is our pre-stressed construction spec. We have our CPAM chapter 10.2 for our consultant CEI inspectors. That pertains to pre-stressing, pre-stressed construction. We also have design standards, or standard plans as they're going to be called now, for pre-stressed girders. There's software that exists that's published by the DOT. This is software that I've had the chance to work on at an earlier point in my career. Also, we must have the producers that we pre-qualified to do this work for us. So there are many different aspects, many different disciplines that are involved with this construction. We have design, materials, and construction. We all work together We all have our respective areas that we get involved with. This is a shot of our first page of section 450, our prestressed concrete spec. This is 10.2 of CPAM for our consultant CEIs that are doing inspection. This is an example drawing from our design standards, or like I said, what will be called standard plans in the future moving forward. Shows the typical reinforcing that you would have for a standard beam. And as I said, we have software that helps designers do computations and calculations for bridge designs. These glowing starred areas are where we have fabricators in the state that do pre-stressing for us. We have within the state, as well as outside of the state, pre-approved fabricators that do these products for us. We have a location near us in Tallahassee, one in Leesburg, Florida, and we have also one in Tampa. There are various others, but these are some of the ones that do pre-stressed beams. So as a practical exercise, if you will, I want those of you out there to take a guess as to how much force does a beam actually need. Well, let's look at these beams, for example. So as we said before, the yield strength of strand is about 240,000 pounds per square inch. Now, when we go to pre-stress these elements, are we going to pull these strands to that point? Are we going to pull them to yield? Well, no, we're not. We're actually going to pull the strands to about 75% of their ultimate strength, or about 83% of their yield, which is somewhere in the neighborhood of 200,000 pounds per square inch. So we don't want to yield these things, but we do want to get the benefit of the material. So you can do, if you know what your area is for a strand, you can compute what this force is. And ultimately, what we put on each strand is in the neighborhood of 42,000 pounds initially on each one of these strands. So if you were to count these strands and do a rough estimate of the resulting compression at the end of this beam, you would arrive at about 2 million pounds of force, or 1,000 tons, that are on these beams. So that's quite a bit. So simply it's the force of one strand multiplied by the total number of strands. So it takes a good bit. So it's a good thing that we've got this material that's able to perform in such a way to do this, to span the spans that we need here in the state. And here's an example of the technology and the historical arch being kind of married together perfectly. This is the Natchez Trace Parkway Bridge up in Tennessee outside of Nashville. So you've got post-tensioned arch with post-tension superstructure. Post-tensioning is basically the same thing as pre-stressing, however it's more so as to when the force is applied. So again, relating it back to the Office of Construction, we update specifications and CPAM Chapter 10.2. We handle issues as it relates to deficiencies in girders, whether they be RFIs or RFMs, RFCs, which are requests for information, modification, and correction, respectively. We will review repair procedures as well as calculations. We may review erection plans and shop drawings. And our office also deals with estimate and payment of these girders, which are done on a linear foot basis. With that being said, I appreciate everyone's attendance, and I welcome any questions anyone has for me at this time.
John, can you remind us why concrete is reinforced? And can you explain a little bit further as it relates to this topic?
Sure, Dave. Virtually every concrete element you see in the constructed world is reinforced with steel inside. As I said before, steel aids concrete in the areas that it is weak in. Zones in concrete that experience tension, or pulling apart, if you will, require the addition of steel. Not only that, but because concrete can expand and contract as temperature increases and decreases, additional reinforcement is required to restrain the concrete from cracking due to these temperature fluctuations.
You talked a lot about steel, but what about concrete? What is it exactly, and how is it produced?
Concrete is made from several types of materials, the basic recipe being large aggregate or stone, fine aggregate, Portland cement and water, which when mixed together cause a chemical reaction to occur, which hardens or cures it. This basic recipe can take an infinite number of variations depending on how you want the concrete to behave as it's mixing, curing, or in its final state. Stated another way, the concrete mix can be tweaked to lengthen the time it takes to cure or harden, manage the temperature the concrete will rise to, as overly high temperatures can have negative effects, or change the compressive strength of the concrete in its hardened state.
You mentioned post-tensioning during the presentation. Is there a difference between pre-tensioning and post-tensioning?
Yeah, I did mention post-tensioning in the presentation, and that's a good question. Post-tensioning, or PT for short, is used to pre-compress fully cured concrete elements prior to them being fully loaded in their service condition. So oftentimes, as in segmental bridge construction, you'll have elements that are precast that are pressed together with post-tensioning. Post-tensioning is applied after the fact, if you will, whereas pre-tensioning is applied as the concrete is curing. So the big difference is that pre-stressing strand is completely bonded to the inside of the concrete. Now, you can also have post-tensioning applications where you have the post-tensioning that is bonded to the inside as well, but primarily it differs in really, it has most to do with where you are applying the stress. Post-tensioning is anchored on either end of the element, whereas pre-stressing, the stress transfers to the concrete internally.
Can you go over what stress is again?
Sure. No doubt you hear mention made of pressure, or PSI, or pounds per square inch from time to time, whether it is watching a movie, a science program, going to the mechanic, or even on the news when you watch the weather forecast. All stress is a unit of force over a given area. Simply stated, 1 PSI is equal to 1 pound per square inch of area. Oftentimes we need to rationalize what a stress is by finding what the force component is on a given area. In the case of a pressure of 1 psi, it is 1 pound of force applied to an area that is 1 inch squared. In this case, a square that has sides of 1 inch by 1 inch.
How do engineers choose what type a bridge will be? I have seen some are made from steel, not concrete. What goes behind selecting a bridge type?
Typically, the bridge type is based primarily on cost and economy. When an engineer begins investigating bridge options, he or she looks at what is the most economical material that can safely span a given length. The engineer will use the safest, most economical arrangement of material and material amount to get the job done. Pre-stressing is oftentimes the bridge type of choice in Florida given its economy and function. Sometimes, a bridge must have a certain look or incorporate aesthetics, in which case the extra cost is built into the project to cover the premium expense. Other aspects which may affect what a bridge type will be includes geometrics such as curves, environmental conditions such as being near the coast or traversing a waterway, which requires the bridge to either be very tall or, if not very tall, movable, or a bascule bridge, if you will. Process in the Florida DOT of vetting these various bridge types is called the Bridge Development Report, or BDR, which is done in the preliminary stages of bridge design for a project.
That's it for now, folks. Until next time, buckle up, travel safe, and always keep moving at the speed of ideas on the Knowledge Transfer Exchange. See you next time. This has been a production of the FDOT Construction Training Development Team, building bridges to the future, one mind at a time.